Okay, this is the solution video to assignment 2. So here we have a man standing in front of a mirror as shown in the figure. His eyes are 1.65 meters off of the floor. So I'm going to go ahead and make note of that right away. So from here down to here, that is 1.65 meters. Okay, and we know that the top of his head to his eyes, 0.13 meters. Find the height above the floor of the top and the bottom of the smallest mirror, in which he can see both the top of his head and the bottom of his feet. So what we are looking for is this height and this height. We're looking for both of those. And then lastly, how is the distance related to the man's height? We'll figure that one out towards the end. For now, though, we know that this incident and reflected ray, this pair, so the incident right here and the reflected ray here, we know that if I were to draw a normal right here, these two angles are going to be the same. We know that. And because of that, we know that this angle where that light ray coming from the foot going to the eyes, where that hits the mirror, is exactly halfway between his feet and his eyes. So this bottom part that I'm going to label H1, height 1. The other one I will label H2 for height 2. Here, I know that H1 is going to be equal to 1.65 meters divided by 2. So that means that H1 is going to give me 1.65 divided by 2 equals 0.825 meters. 0.825 meters. So, we know one of the two heights now. Height 2. Now, this one, if I extend this original line I drew from his eyes all the way across, I see that the mirror actually goes a little bit above where his eyes are. So I know that the top of this mirror is going to be a little bit more than 1.65 meters. And I know it'll be a little bit less than 1.65 plus 0.13, so his full height. So the top of this mirror is a little bit less than the person's full height, but a little bit more than where his eyes are. Now, again, using the same logic, light coming from the top of his head will reflect back off the mirror at the same angle that it comes in at. So the top of this mirror has to be halfway between his eyes and his head. So that essentially tells us that this little distance right here is going to be half of 0.13. That little distance right in there. And that is the distance above where the person's eyes are. So for H2, we know that it is going to be the height up until where the person's eyes are, plus this little addition above, which, as we just said, is 0.13 divided by 2. So H2 is going to give us 1.65 plus 0.065 equals 1.715 meters. up off the ground. Awesome. Now, for the last chunk, how is this distance related to man's height? Now, because of the wording, I accepted a couple of different answers here. I did not word this as well as I should have. Some people said that the distance from the person to the mirror here doesn't matter at all, which is completely true. So I give you the mark if you said that. Or, but what I was actually looking for is how does this distance, the length of the mirror, relate to the man's height? If you go through and do the subtraction here, 1.715 minus 0.825, you get, so h2 minus h1 equals 0.89. And if you take the man's full height, which is 1.65 plus 0.13, so 1.65 plus 0.13 equals 178.78. And if you take 1.78 divided by 2, you get 0.89. So this top circle that I just circled is the height of mirror, length of mirror. So length, that is not the word length. Length of mirror is this guy. And this is half the person's height. And you see that they are exactly the same. I should add meters to both. There we go. So in this case, the meter is exactly half the person's height, and it is placed at, the bottom of it is 0.825 meters above the ground, and the top is 1.715 meters above the ground. So that is question 1. Question 2. Explain the difference between diffuse and specular reflection. Provide one example of each in your answer. So over here I will do diffuse, and over here I will do specular. In diffuse, reflected light I'll say light gets reflected. I'll word this slightly differently. So I will say that light gets reflected in many different directions. In many different directions. Impeding the creation of an image. An example is frosted glass. You can't see your own reflection in it. You can't really see through it at all. It blurs it. It's like a rough texture if you touch it. Light rays coming in to hit it, even if they're parallel, will bounce off in all crazy different directions. For specular, in this case, light gets reflected predictably. So yeah, let's say light gets reflected predictably, or, yeah, start a new sentence here. Light gets reflected predictably. Oh my gosh, words. So, parallel, I'm going to run out of room. Parallel incident light reflects and remains. And remains parallel. Example, just a traditional mirror. So specular light rays coming in parallel will be reflected off and stay parallel, but in diffuse, parallel light rays coming in will be reflected off in different directions. Number 3 here. A laser beam strikes a plane mirror at an angle of incidence of 35 degrees. Calculate the angle of the reflected beam and sketch a diagram of the problem. So in this case, I'm going to sketch my diagram first here. So this here is the normal that I've drawn. This here is the mirror. And I said 35. And it's measured from 90. So that will be 125 here. There we go. And my incident light ray coming in. And that will be 55 coming out. So theta R for reflected ray, theta I for incident ray. So angle of incidence, angle of reflection, and normal are all labeled in my diagram here. And we know that the angle of incidence equals 35 degrees. We know from our law of reflection that the angle of incidence is equal to the angle of reflection. So therefore, the angle of reflection equals 35 degrees. They are even. They are equal. So that is question 2 and 3. Question 4. Using the ray model of light, explain why we can assume that the light from the sun that reaches Earth is parallel, even though in reality it is not. So in this case, we have our sun, we have our Earth, and the sun is giving off light rays in every direction, no matter what. And the light rays that actually go and reach Earth, because of this huge distance, because of this huge distance, Earth is a teeny tiny little target. So any small change in angle of the source light ray will result in a huge difference by the time the light gets to Earth. So due to the large distance between the sun and Earth, due to the large distance between the sun and Earth, a small change in angle results in a light ray I'll say either missing or hitting the earth. Therefore, we can say, therefore, all light, I should say all sunlight hitting earth. Let me just shrink this down a little bit. Therefore, all sunlight hitting earth is so close to being parallel that we can assume it is. Looking back, this is known as paraaxial approximation. So looking back in the lecture notes, that's what you should keep an eye out for. So in this video, I won't show it on this video recording here, so it'll be up to you to go reference that video if you want to take another look. In the video, a person approaches a mirror, or you can see basically the same thing in a shiny, not too scratched up spoon. Something that gives you specular reflection and not diffuse will work. The person starts off inverted, and they get larger and larger and larger until you hit the focal point. And once you pass the focal point, the image flips. And then as you get closer and closer and closer, the image becomes closer and closer to the real size of the object. In this case, this is the person. So, as you approach, the image gets larger. I should say the inverted image gets larger until the person passes the focal point where the image flips and is now upright. The reason the image attitude changes is because the person passes the focal point. So, why does the image attitude change? The person passes the focal point. That's what I was looking for there. B, choose a point in the video and determine what the salt image characteristics are at that point. In front of the focal point or between the focal point and the mirror. Just two examples there, really, of what you could have chose. I'm going to choose in this, I'll do a little diagram showing what I'm doing. This is C, this is F, this is the mirror. I'll do one for the person being right here. Most people did a salt image characteristics for an object right here, so that's why I'm choosing this. So this is for an object between the focal point and the mirror. That is what I am doing here. In this case, the image, I guess I'll draw it in green. Now, because it doesn't specify, I was happy to say I was taking same as a correct answer because I didn't specify how close, and I wasn't requiring you to anyway. Same or slightly larger. Attitude is upright. Location is behind the mirror. Or right of mirror. And type in this case is virtual. If you chose the other outcome, it would have been either smaller or larger, depending on where exactly you said you were. It would have been inverted. It would have been in front of the mirror. In this case, the image depends on whether your object is between the center and the focal point, or in front of the center, or to the left of the center. And in all of those cases, the image would be vertical, or not vertical, real instead of virtual, is what I meant to say. So that is number 4 and 5. And I see I did number 5s again. So this is actually number 6. And 6. Okay, sorry. I did not notice I did that. So 2 number 5s. Okay, well, number 6 actually. That's what this actually is. So in this case, we have object distance. We are told that that is 2 meters. So a pinhole camera is set up so that the distance from the object to the pinhole is 2 meters. The distance from the pinhole to the screen of the camera is 4 meters. And the height of the object is 0.4 meters tall. We don't know what image height is equal to. We are asked what magnification is equal to. In this case, we know that magnification is equal to image height over object height. And we also know it's equal to the negative of distance image over object image. So we have these two equations for magnification. Now, we don't know what image height is equal to. We don't know this. Now, some people went ahead and used just this portion of the equation and solved for image height, which is fine. You can totally do that. But I don't ask you to. So a little bit of extra work. In this case, though, I am going to use the negative image distance over object distance because I have both of those numbers. So in this case, we have negative 4 meters, and this is a positive distance because the image distance is on the right-hand side of our pinhole, and our object distance is also positive because the object is on the left-hand side of our pinhole. So if I go ahead and do that math, I get m equals -2. Now, do note the units cancel out. So magnification was -2 for that problem there. If you went ahead and calculated image height, that is not an I. Image height, you should have gotten -0.8 meters, which is exactly -2 times the object height. So if you did that, great job, good for you. Sorry I couldn't give you extra marks. It's not what I was asking for, but good for you if you did that as well. And lastly, what are the salt image characteristics of the image formed in this pinhole camera setup. Now, it is larger, as we just mentioned. Our magnification makes the number larger, so the image is larger. Also in the image, it's very clearly larger in our diagram up here. Very clearly larger. Attitude is inverted. Again, you can tell just by looking at the diagram, or by the fact that the magnification is negative. So the magnification is negative. I will say less than 0. The larger magnification is greater than, I'll say the absolute value of the magnification is greater than, absolute value of the magnification is greater than 1. And absolute value, just so you know, means that when you sub in the number, you just ignore the signs or switch it all to positive. So absolute value bars, that's what those two vertical lines mean. Absolute value just means consider the positive case, ignore the sign if it's negative. Location, this is behind pinhole or right of pinhole by 4 meters. And the type in this case is real. The real light rays going from the object collide with the real image. So we have a light ray going here, a light ray going here. We have all the other light rays going in between as well. They actually do collide with the screen on the back of the pinhole camera and create a real image. So in this case, it's not virtual. In virtual, you have to trace back like an imaginary reflected ray. So that was assignment 2 solved. Any questions, please email me. See me.